Okay, so last class we are discussing canonical transformation. Canonical transformations. Okay, so last class we did problems mainly. Okay, mainly our problems focused on finding whether, checking whether a transformation, a given transformation is canonical. Okay, so we did it in two methods. We said that we can check by looking at the Poisson bracket, the fundamental Poisson brackets. All right, the fundamental Poisson bracket relations have to be satisfied. Okay, and also I said this could be taken as a definition of canonical transformation. Right, canonical transformation from PQ to capital P, capital Q can be defined. Okay, this can be called a canonical transformation if the fundamental Poisson bracket relations are the same. Okay, that's one way to define the canonical transformation. We defined it using generating functions. Both are equivalent. You can solve problems using both methods. Okay. Now, we said that there's another way to solve this. We said that you check this combination. Okay. I think I'm writing it correct. P, D, Q. Okay. If there are a number of them, you'll have to sum. This is capital. Okay. This has to be a perfect differential. Right? And in some problems, we could identify the generating function from this. Okay, because we know this is a perfect differential. You just remove that D and you get the generating function. And using the transformation equation, you can get it in the necessary form. Okay. Sometimes it gets complicated. So we need to discuss a method to find the generating function if we need to find the generating function if the transformation is given. All right. So that's the kind of problems we'll be looking at today. Right. Finding generating function when canonical transformation is given. Okay. All right. One method we already discussed. You just take P dq minus P dq, and that's a perfect differential for a canonical transformation. You can just integrate it. All right. Let's look at a more general or alternate method. Okay. Or let's discuss a few steps to find the generating function. Okay. So for example, okay, there are 4 types of generating functions or mix of them. Let's take the first type. All right. So suppose you explicitly need the generating function of the first type given a transformation. Right. How do you find the generating function? Right. Now, step 1, we know that df. Okay. This is just an example. Right? This is true for all cases. This is equal to dou f by dou q dq plus dou f by dou capital Q dq. Okay. All right. Now this we know. All right. Now we need to know these equations. We said there's a trick to know this. You always write the old coordinates first and the new coordinates second. So it's easy to remember. All right. We know that dou f by dou q is plus p dq plus dou f by dou capital Q is minus, am I right? Minus capital P dq. All right. You do this. Okay. Now the next step, this is let's say step 1. Okay. Step 2. The next step is we need a generating function depending on small q and capital Q. It could be small p and capital P, however, the method is the same. All right. So in that case, the step 2 is to write this df. Okay, you use the given, the canonical transformation is usually given. You use the given canonical transformation to write this small p as a function of small q and capital Q, because this is the functional dependence of the generating function that you need. Okay, minus capital P of, you write it in terms of small q and capital Q. Whatever functional dependence you need, you use the given canonical transformation to find these relations. Okay, this is and dq. All right. So from then the next step, we will see this in action. The next step is to see, you equate this. All right. You see that you have got one equation here. Dou f by dou q is equal to p of q comma q. All right. Is this fine? we have got one more equation. Dou f by dou q. You just compare this, all right? Because we are talking about df. Okay. So you just compare this. This we obtain from the given question or the given information. Okay. Dou f by dou q is equal to minus p of q comma capital Q. Okay, that's the third step. The first step is to integrate this. Okay, you need to integrate this. So from here, you can take this as a differential equation and integrate this. All right. So you find f is equal to integral p q comma capital Q. All right. You can choose whichever integration is simpler. All right. dq. Okay. Is that all? No, because this will give you only the dependence on small q. Right, this is only an equation for the dependence on small q. There could be an arbitrary general function f of capital Q. All right, these are constants. Basically, in usual integration, we add a constant here. Okay, but since this partial derivative, okay, it's a derivative with respect to q only. Okay, with small q only. When you take partial derivative with respect to small q, you keep capital Q as constants. Am I right? So you can have a general function of capital Q over there. All right. Now you can determine capital Q by okay. So now you can determine. Now what you do is that next you find this equation. You construct this equation from this S. Okay. Now then step 5. This is only part of the solution. Okay. This is only part of the solution. For the next thing, what you do is that you take this f, capital F, all right, and find dou f by dou q and equate it to minus p of q comma q. All right. Sometimes you may need to integrate, but usually this would completely give you the solution. All right. These are the 5 steps of doing it. Okay. I'll repeat. Whatever kind of functional dependence you need for your generating function, all right, you write it like that, and then you do this thing. And the important thing is that this p and p or p and q, whatever comes up here, you write it as a function of this functional dependence. All right, then you just integrate. All right. So when you integrate, you have to be careful. You should know that when you integrate, this is a partial derivative. There can be a general function of capital Q. This could be a constant, but it need not be a constant in all problems. So you have to be careful. Okay. So let's do these kinds of problems. A few problems of this kind. Okay. So this also can be asked. They can just give you a transformation and ask you what's the corresponding generating function. Okay. And this method is good. We can use it to find any type of generating function for a given transformation. Right? A given transformation can be obtained from a number of different generating functions. All right, because all these generating functions are connected by a Legendre transformation. So let's see an example. All right, let's look at an example. We have got this transformation Q equal to P inverse. Okay, and capital P is equal to Q P square. Okay, this is the transformation. Find let me see the question. Find. They are asking find f of q comma q. They're asking you to find the generating function of the first type, which will give you this transformation. Okay. Now, how do we do this? First step, we know that df is equal to dou f by dou q dq plus dou f by dou q d capital Q. Okay, this is dou f by small q, that is p dq plus dou f by dou q is minus p, right? Minus. You remember the trick to understand which with the sign, right? Here q comes in the second place, so you need a minus sign. Minus capital P dq. Okay. All right. Now, what's the next step? The next step is to write the small p in terms of q and q. All right. The next step is to write this small p in terms of small q and capital Q, and capital P in terms of small q and capital Q. Let's find that here from the given transformation. Okay. So you see that small p as a function of q and q. This is equal to small p is just q inverse. Okay, you get it directly from there. Sometimes you may need to solve these equations in order to find this. Sometimes it is simpler. All right. Next, you need capital P. Okay, P is equal to, here it is given as q p square, but we need it as a function of q and capital Q. Okay, so you say this q is fine. We don't need the small p here. You need to write it in terms of capital Q. So this is q raised to minus 2. Is that correct? Yeah. Okay. All right. Now, so you can write df. Now we use this. Okay, we use these things. Small p is simply q inverse, and you have got a dq there. Okay, and minus, this is q raised to minus 2. Okay, dq. All right. Now the third step is to integrate this. Right? We know that from here we know that dou f by dou q. Okay, dou f by dou q is equal to q inverse. Okay, so you compare this thing, dou f by dou q is equal to q inverse. This means that f is equal to integral q inverse d q inverse dq. Okay, it's just like your usual differentiation, df by dq. So you take integral q inverse dq. All right, but that's not all. That's not all. You could have a general function of q. Okay, so you see here the partial differentiation is with respect to small q. Then you will have a with respect to the first thing, right? Then you will have a general function of the second thing here. All right, if it is small p and capital P, like that, whichever way. All right. Now this integration is simple. We treat the old and new coordinates are independent. So q inverse dq is simply q inverse q. Okay. Yeah. Q inverse q. I think we did. Okay. Plus f of q. Okay. Now we need to determine this f of q. How do you find f of q? Right. We know we use this equation now, right? We know that dou f by dou q is equal to this thing, right? It has to be equal to minus p, right? So it's equal to minus q raised to minus 2. Is that correct? Yes, dou f by dou q is minus p. So that's equal to minus q, capital Q raised to minus 2. Okay. Did we do it correctly? Just give me a moment. Yeah. Okay. So plus, so this means that we already found our f here. So you use this f now. Okay. So you take dou f by dou q. So you see that if you take the derivative with respect to capital Q, this becomes minus q raised to minus 2. All right. Take the derivative with respect to capital Q. So minus q raised to minus 2 q. Okay. Plus you also have, you don't know this, you need to determine this dou f by dou q. Okay. This is equal to minus q raised to minus 2. Okay. So this means that what does this mean? This means that you see that these are the same things, right, on both sides. Okay. So this means that dou f by dou q is equal to 0. Okay. Or f is equal to some constant. Okay. Let's say f of q here. F of q here is some constant. Okay. And this constant, okay, it's arbitrary. You can choose any constant and there is no problem in choosing 0. Okay, we can always choose it 0 because we are talking only about derivatives. That constant would not matter. Okay, so this means that we have our generating function f of q comma capital Q. f of q comma capital Q is equal to Q inverse Q. Okay. All right, that's the answer. I hope this is clear. Okay, I hope the steps are very clear. Let's do a few more problems and then it will be better. Okay. Any questions with this method? Is it clear?
Okay.
All right, good. Let's look at another problem. Okay. We have got capital Q is equal to square root of Q cos 2p. Okay. And capital P is equal to square root of Q sine 2p. Okay. All right. The question is this: you need to find f of p comma q. All right. This is the dependence. This is the function that they are asking. All right. So we do the step one. Df is equal to dou f by dou p dp plus dou f by dou q dq. And we know that dou f by dou p comes in the first place. So it is minus q dp plus dou f by dou q. That's also minus, right? Because dou f by dou q is, yeah. So dou f by dou capital Q is minus capital P dq. All right. What's the next step? You need to write small q and capital P in terms of small p and capital Q. All right. So you do that from here. Okay, we do that from here. We have got q equal to square root of q cos 2p. Okay, so you can square it. Q square is equal to q cos square 2p. Okay, so from here you see that q is equal to, you can write q square secant square 2p. Okay, because inverse of cos square is secant square. Right? Now we've got q as a function of capital Q and small p. That's the dependence we need. Okay. Similarly, you see that you need capital P in terms of small p and capital Q. All right. So you see that capital P is equal to, you need it as a function of small p. You have got a small q here. We don't like it, so we substitute from here. All right. Square root of q is q. The square root of q is q secant 2p. Okay. Q sec 2p and sine 2p. That p is fine, right? Because we have this p. So it is sine 2p. Okay. This you can write it as q tan 2p, right? Sine by cos is tan. Okay. All right. So this means that our df can now be written as minus q, that is q square secant square 2p dp minus capital P is q tan 2p. Okay, that's fine. Now we know that this thing can be equated to dou f by dou p. So if you get two differential equations, partial differential equations, dou f by dou p is equal to, okay, dou f by dou p is equal to minus q square secant square. Yes.
അവിടെ previous step ഒരു dq ഇല്ലേ?
ഏതാണ്? ഇതോ?
അല്ല ലാസ്റ്റ് ഒരു dq ഉണ്ടാവില്ലേ?
ഇവിടെ yes, yes, correct. Okay, thanks. So minus q square secant square 2p, and you get one more equation, dou f by dou q is equal to minus q tan 2p. Okay, all right. Now we will integrate this one. That seems like an easy integration. Okay, so you can say from here, you can say that f is equal to, okay, integral, f is equal to integral minus q square secant square 2p, okay, plus, you know that there will be an extra function of capital Q. Am I right? Because you are dealing only with the partial derivative with respect to p here. Okay, so this we can write it as, when you integrate this, this is easier, right? Because this is minus q square, and integration of secant square x is tan x. Am I right? Tan 2p is there a 2 somewhere? Let me check.
നമ്മളൊരു 2 കൊണ്ട് ഡിവൈഡ് ചെയ്യണ്ടേ?
Yes, tan 2p divided by 2. Okay, that's correct. ശരിയല്ലേ? Because integration of secant square x is equal to tan x. Okay, so if you take x equal to 2y, you get secant square 2y integral 2. So integral secant square 2y dy will be tan y divided by 2. You're right. Okay. All right. So we've got one part of our generating function. Okay. Now this also is a function of capital Q and small p, but there could be in principle some function of capital Q over there. All right. So then you use this equation. Okay. We also have dou f by dou q is equal to minus q tan 2p. Okay, so you check this. This means that minus 2q tan 2p divided by 2 is equal to plus dou f by dou q, right? Is equal to minus q tan 2p. Okay, so this gets cancelled. You see that minus q tan 2p there and minus q tan 2p there. Again, you see that f of q is a constant. Okay, again, as in the previous case, but you cannot assume that this is the case always. Okay, in many cases this is true, but you cannot assume this thing. Right? Dou f by dou q is equal to a constant. Sorry, is equal to 0. Is equal to 0. So you can, this means that f is equal to constant and you can set it equal to 0. This means that our generating function is f is equal to minus q square tan 2p. That's it. Minus q square tan 2p divided by 2. Okay. All right. That's the generating function. So this is easy to do. If you get, if you do 1 or 2 problems, then you know how to do these things. Okay. Okay, let's do this thing quickly now. P is equal to m omega q cot q. Okay, and capital P is equal to m omega q square divided by 2 sine square q. Okay, find f of q comma capital Q. Right, so the dependence is given. So we proceed. This is easy. We have already done this. So let's be a bit quicker here. We know that df is equal to dou f by dou q dq plus dou f by dou q dq. Now this has to be equal to dou f by dou q is small p dq plus dou f by dou q is minus capital P dq. Okay. Now we need to write the small p and capital P in terms of small q and capital Q. Right. So you see that it's already in that form. Right. Small p is written in terms of small q and capital Q, and capital P here is written in terms of small q and capital Q. So we already have it in the necessary form. Yes.
കഴിഞ്ഞതിനകത്ത് നമ്മൾ ഡി എഫ് മൈനസ് ക്യൂ ഡി പി മൈനസ് പി ഡി ക്യൂ എന്നാണ് കൊടുത്തത്.
മനസ്സിലായില്ല. ഏതാ കഴിഞ്ഞതിന് തൊട്ട് മുമ്പത്തെ പ്രോബ്ലത്തിലോ?
കഴിഞ്ഞതിനകത്ത് ഈ സ്റ്റെപ്പിന് തന്നെ ഡി എഫ് എഴുതിയപ്പോൾ മൈനസ് ക്യൂ ഇൻറ്റു ഡി പി റിവേഴ്സ് ആയി നെഗറ്റീവ് സൈൻ കൊടുത്തു.
ഇങ്ങനെ എഴുതുക അല്ലേ? 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 That's because this f is a function of p and capital Q. Okay, this is type 2, I think, or type 3. Okay, so if you look at that, you will see that
It's
dou
type
F
3.
by dou P is minus Q, and
Mhm.
dou F by dou Q is minus P. Okay. In this case, this is what do you say, the first type. So dou F by dou Q is small p, and dou F by dou capital Q is minus p. That comes from the.
Okay.
Now
Thank you.
I had given you a way to remember this, right? So you inside this argument of generating function, you always write the old one first and the new one second. Okay, this is done.
മനസ്സിലായി.
Sign എങ്ങനെയാ എടുക്കുന്നത് ഓർമ്മയില്ലേ? Alright, so അത് explain
ആദ്യം Q
ചെയ്യണ്ടല്ലോ.
വരുവാണെങ്കിൽ പോസിറ്റീവ്.
Yeah,
വേണ്ട.
exactly, yes.
Thank you.
Okay, all right. So we already have it in this form. So this is m omega q cot q dq minus capital P m omega q square divided by 2 sine square q dq. Okay, so you take this equation. We have got two differential equations now. We say dou f by dou q is equal to m omega q cot q, and we also have dou f by dou capital Q is equal to minus m omega q square divided by 2 sine square q. Okay, now you integrate this. So you see that f is equal to m omega q cot q integral. All right, it is dq, and plus you have some function of capital Q. All right, so this is equal to this is also easy because it's an integration with respect to q. So this is m omega q square by 2 cot q plus f of q. Okay, now you use the second equation. This is our generating function. It's still not completely determined. Okay, so we need to find whether there's an extra function of capital Q or whether that's a constant. Okay, so for that we do this step. Dou f by dou q is equal to, so this is capital F and this is small f, right? And we know that dou f by dou q is equal to minus m omega q square divided by 2 sine square q. Okay, that's equal to oh, sorry, yeah, that's correct. So you take the derivative of this, so it is m omega q square by 2, and cot q, derivative of cot q is minus cosecant square q. Am I right? Plus dou f by dou q is equal to minus m omega q square divided by 2 sine square q. Okay, so again you see that it's the same. This is the case always. I want. All right, so you see that it's again the same thing, right? Yeah. Okay, so again f is equal to a constant, so we can take it equal to 0, and our function f is equal to m omega q square divided by 2 cot q. Okay, right. Now this method can be used in any way, right? If you are careful to do these integrations by writing the extra thing as f of q or f of p, whatever, then it's easy to do this. You need not always write it in exactly the same way. Okay, you can do the complete integration, and then in the end you can make the substitution, etc. Okay, these things are possible. I think this problem we had done in the class to check whether this is a canonical transformation. We had checked that this is a canonical transformation. Okay, but we didn't get the generating function, so I'll give you the generating function now. So that seems a bit complicated, but let's see if we can solve it. Okay. The question is find f of q comma p, right? So they say f of q comma p. Let's write it as f of p comma q, so that we can write it. We can remember the minus sign. Okay, so let's start. We need f of p comma q. All right. Okay, so we have got df dou f by dou p dp plus dou f by dou q dq, right? So this is equal to dou f by dou p is minus q, okay, and dou f by dou q is minus, okay, right. Should be there. Now we need to write small q and capital P in terms of these things, and for that we'll have to invert that equation. Okay, let's invert this equation. We need small p, small q, and capital P in terms of small p and capital Q, right? Okay, so let's do that. So from here you see that e raised to q, okay, this is equal to, we just need to invert this to find small q. Right? So e raised to q is equal to 1 plus square root of q cos p, okay, and yeah, so yeah, e raised to q minus 1 is equal to square root of q cos p, okay. So you see that q is equal to e raised to q minus 1 square secant square p, just square on both sides, okay, and you bring it to the other side. So we've got small q in terms of capital Q and small p. That's what we need. Okay. We also need capital P in terms of small p and capital Q. Right. So let's also do that. So from here you see that P is equal to. So we just need to substitute for the small q here, right? The rest of it is in the correct form. Okay. So let's see, this is equal to 2, 1 plus, okay. So you've got a square root of q there. Square root of q we know from there, it's e raised to q minus 1, okay. And we have got a secant p and a cos p there, okay, which is equal to 1. So I don't have to write it. Okay, that's equal to 1. Okay, and you also have a square root of q there, which is again e raised to q minus 1, raised to q minus 1, secant p sin p, right? Secant p sin p by cos p, which is equal to tan p. All right, so this is, we can further simplify this. 2, 1 minus 1 get cancelled, so it is 2 e raised to q multiplied by e raised to q minus 1 tan p. Okay. Yes. Now we proceed. We know that dou f by dou p is equal to minus q. Okay, so it's equal to minus e raised to q minus 1 square secant square p. Okay, so f is equal to minus integral e raised to q minus 1 square secant square p dp, plus you will have a function of general function of capital Q, right? Okay, So I'm following this method so that this is more general, right? You always have to be careful about this extra term. And in the cases, the way we have arranged them particularly means that in all the cases, this f becomes a constant, all right? So when you do actually problems, you can just find this integration, assume that the other one is a constant, all right? But you have to check whether you get the correct transformation equations, whether the derivative will give you the p term, all right? So that you have to check, that's enough, right? So, yeah. Right, so how do we integrate? So it's an integration with respect to p, it's easy. So this is e raised to q minus 1 square. Integral secant square p is? Integral of secant square p is tan p, am I right? Yes. Tan p plus f of q. Now we can take this f of q as a constant and just check. Okay. Right, we can just check whether this is true. Let's take f equal to minus e raised to q minus 1 square tan p and just check, all right, whether what was the other equation we needed to check? Dou f by what was the other equation? I think I removed it. Dou f by dou q, right? Whether this is equal to minus p. Okay, so you check this. You check this. It's easy, it's easily checked, right? Because you take the derivative, you get to 2 here, 2 e raised to q minus 1. It's correct, right? Which means that this f again can be put equal to 0. It may not have any dependence on q, right? So you remember it's always to check this thing, all right? If you mess up with the functional dependence somewhere, you can still get it correct finally by including this term. In the way that we have constructed, this term always can be set equal to 0. Right? So you need only to do one integration, but always check, right, whether the derivative gives you the other function also. Okay. All right. And there is another model of problems that we have already done implicitly in these things. But sometimes the generating function is given and you need to find the canonical transformation. Okay. So if possible, you should write the new coordinates as a function of old coordinates, which means capital Q as a function of small q and small p, and capital P also as a function of small q and small p. Okay. So let's do that. This is another model of problems using canonical transformation. So we need to find the generating function. We need to find the generating function. No. Sorry, we found the generating function. We need to find the transformation equation. So that we need to find the canonical transformation if generating function is given. This is very easy. I'll be very quick because we already are kind of masters in this, right? Because f is equal to q e raised to capital Q. This is a function of, you write the functional dependence, just to be careful, q comma capital Q. All right. Now it's easily done because you know that small p is equal to dou f by dou q. Okay, that's equal to e raised to q, and you know that capital P is equal to minus dou f by dou q, and that's equal to minus q e raised to capital Q. All right. Now this may not be in the exact form in which your options are given. You should be able to invert these equations. Right. So you see that capital Q. So this you can write it as small p is equal to minus q. Okay, let me check. So if we can write the old coordinates as a function of, sorry, the new coordinates as a function of old coordinates, it's better. Okay. All right. So you see that this is already the P. Let's write it as Q comma. Oh, sorry. So we can say Q, you can just invert this as a function of old coordinates and momenta. That's simply equal to log P from here. All right, you just take log on both sides. And from here, you see that capital P as a function of Q comma P is equal to, in terms of the old coordinates, that's equal to minus Q, and e raised to Q is already P, right? So minus Q P. These are the transformation equations. Okay. So this is easily done. Let's do another one. Okay. F is equal to, I'm going a bit fast. If there's any doubt, you can ask. Tan Q. All right. We see that this is a function of Q comma capital P. Okay. This Q comma capital P. And you know that P is equal to dou F by dou Q, and capital Q is equal to dou F by dou capital P. Okay. So you just do this. Dou F by dou Q is equal to P. What's the derivative of tan X? What's the derivative of tan X? It's secant square X, right? Right? Yeah, it's capital, what am I finding? Small p. Let's do it here. So small p is equal to dou F by dou Q. So it's capital P secant square Q. Okay. And what do we have for capital Q? Q is equal to dou F by dou P. Okay, that's simply tan Q. Okay. So we can write it as a function of old things. So we have already have capital Q is equal to tan Q. Usually it's asked in this form. Okay. Let's just be, these are known as the transformation equations. Okay. And capital P of Q comma P. This is how you find the transformation equations. Okay. Capital P of small Q comma P. What is it? So if you take this P here, you just need to invert it. So it becomes P cos square. Okay, just take this to the other side. So it becomes P cos square Q. These are the these are the transformation equations. Okay. Again, we have another question. F equal to lambda Q square cot Q. Okay. This is F of Q comma capital Q. You know what to do. You know that P is equal to dou F by dou Q. It's easy to remember, isn't it? And capital P is equal to dou F by dou Q. Right. And I'll just give you the answer. You take the derivative. It's a derivative of cot Q is minus cosecant square Q. All right. And the answer you get is this. We have got Q is equal to cot inverse. You can check this, all right? This is the answer I got.
Capital P or negative കൊടുക്കണം സാറേ.
Ah, you're right. Yes, good. Good. Okay. Yeah, that's correct. And Q is equal to cot inverse. You know how to take the derivative, all right? And there is also this relation. Q is equal to square root of P by lambda sine Q. Now, if you can invert it, you invert it. Otherwise, leave it. Okay. Depending on the option that you are given, you may have to change the form, right? Whether it's whatever is the transformation equation. Okay. So such problems are also there. I'll give you another question as a homework. Okay. We have got F is equal to minus e raised to Q minus 1 square tan P. You already know the answer, I think, because this generating function we found from a given transformation. Okay. But yeah, you write either the new coordinates in terms of the old one or the old one in terms of the new one. Okay. So the F is equal to F of P comma Q. Right. I think you can do this easily. Now I'm asking you to find. So this is, you see that Q is equal to minus dou f by dou p, and capital P is equal to minus dou f by dou q. Okay, to just do this, and I want you to find P of q comma P. Okay, the old coordinates in terms of the new coordinates. You can call it the inverse canonical transformation if you like. Okay, and q of q comma P. Okay, you find this. So I think it's exactly the same steps. There's nothing catchy in there. So I'll just continue. Right? You can try this. This is the question asked. Okay. All right. Now we'll do another class of problems that can be asked from this thing. All right. We need to find the transform Hamiltonian. Finding the transformed Hamiltonian. So here is a question. A particle of mass m moves in one dimension in a potential V of q. Right? There's a mass m and it's moving in a potential V of q. Retarded. It's called retarded. Yeah, there's a damping force. There's also a damping force minus 2m gamma q. Okay. It's Lagrangian. So Lagrangian is already given. L equal to e raised to 2 gamma t half m q dot square minus v of, that's the Lagrangian. So now it's the old steps all over again. You find the Hamiltonian first and then, okay. So this is the question. Now the questions are this: find the corresponding Hamiltonian. Okay. And there's a second part for the question. For the generating function, f equal to e raised to gamma t q p. Right, the generating function is time dependent. Right, usually all the cases that we did, it's not time dependent. So the Hamiltonian and the other thing are the same. The transformed Hamiltonian are same. But here you see that for the generating function f equal to e raised to gamma t q p, find the transformed Hamiltonian. Find the transformed Hamiltonian. If V of q is equal to half m omega square q square. Right. So the first part of the question is simply to find the Hamiltonian. Okay. All right. So how do you find the Hamiltonian? Can we write it as the total energy here? Can we write it as the total energy? Okay. Yeah, because there is no velocity dependence on potential, etc. You can write it as the total energy, or you can do the usual steps. All right. You just do this. It is p q dot minus L, and you need to find again when we need to find p. All right. Let's find p. P is equal to dou L by dou q dot, and that's equal to e raised to 2 gamma t. Okay, this is mq dot. Okay, or we know that q dot is equal to e raised to minus 2 gamma t multiplied by, we bring it to this side, p by m. This is what we need because we shouldn't have any q dot in our new Hamiltonian. Okay, now this is the Lagrangian. So let's be careful and do it in the usual way. Okay, this e raised to 2 gamma t there may be a bit confusing, so let's do it. All right, so let's find q dot p minus L. Okay, that's equal to, we already have q dot p there, e raised to minus 2 gamma t, and you have got p square by m, right? Because there's a p there and a p by m there, right? Because there's a p there, minus L, okay, half m. What's q dot? Q dot square is e raised to minus 4 gamma t. Okay, you need to find q dot square, and you have got p square by m. Okay, and minus v of q. V of q is fine. Right. Now this is equal to e raised to minus 2 gamma t p square by m.
P square by m square ഉണ്ടാവില്ലേ?
Yes, you're right. Okay. All right, that's correct. So this gets cancelled. Okay. And you see that this is simply e raised to 2 gamma t. You just subtract this, all right? Because of the 2 gamma t there, it cancels the 2 e raised to minus 2 gamma t there. You get exactly the same. So this you can pull outside, and it's p square minus half p square by m. P square by m minus half p square by m. So it's simply p square by 2. Okay. Plus e raised to 2 gamma t. That's also there. All right. So this is our Hamiltonian. Yes. Okay. Now we need to find the transformed Hamiltonian. We need to find the transformed Hamiltonian for a generating function. We say we are given the explicit v of q. If v of q is equal to, what was v of q? Half m omega square q square. All right. If that's the v of q, we need to find the transformed Hamiltonian. So Hamiltonian is now e raised to minus 2 gamma t p square by m. Okay. Plus v of q we will have here. Okay. V of q is half m omega square q square e raised to 2 gamma t. This is fine. And the generating function was given. Generating function of the canonical transformation was given. It's equal to e raised to gamma t q capital P. All right. Okay. So how are the old and new Hamiltonians connected? We know that if the generating function is not time dependent, then the old and new are the same. You just need to change the dependence. All right. Here it is time dependence, and we know that it's connected by this relation. K is equal to h plus dou f by dou t. All right. So that is equal to p square by 2m e raised to minus 2 gamma t plus e raised to 2 gamma t m omega square q square divided by 2. Okay. Plus dou f by dou t. Dou f by dou t is gamma q p e raised to gamma t. Am I right? Okay. Now, is this the correct answer? Is this the correct answer? Is this the correct answer? Can we write it like that? Is this fine? Is it okay? Or is there something else that we need to do? All right, we cannot write it like this because there's a small p and a small q sitting there. We shouldn't have them. We should only have capital P and capital Q inside the transformed Hamiltonian. All right, this thing is fine. Numerically, it will be the same, but the new Hamiltonian, okay, it is a function of capital Q and capital P. So for this, we need to find the transformation equations for capital Q and capital P. So you again look back at f. You see that f is a function of q comma p. All right. So you see that the transformation equations are q is equal to small p. Small p is equal to dou f by dou q. Okay, dou f by dou q. That's equal to e raised to gamma t multiplied by p. Okay, so instead of small p, you should have e raised to gamma t p, and you see that capital Q is equal to dou f by dou p. That's equal to e raised to gamma t multiplied by q. Okay, multiplied by q. All right. So you can write small q is equal to e raised to minus gamma t multiplied by q. So using this transformation equations, you see that what's p square? What's p square? What is p square? P square is, okay, let's write it like this, 1 by 2m. There's e raised to 2 gamma t capital P square. And here there's an e raised to minus 2 gamma t. They cancel. Okay. So it is actually capital P square by 2m plus, all right. You take q square here. Again, there's a minus 2 gamma t in this q square because it's minus 2 gamma t capital Q. Okay. So substitute there. This term also will go. So it is m omega square capital Q square divided by 2 plus gamma q. Okay, this gamma q, again, you will have to write it as there's an e here. E raised to minus gamma t there. Right, that will cancel with this. So you get gamma q, you have capital Q e raised to minus gamma t, and that will cancel with this. Okay, that's the final answer. Okay, so remember, when you are asked for the transformed Hamiltonian, given a generating function, okay, it's very easy to mistake it. All right, we may stop here, just like we were finding the Hamiltonian from the Lagrangian. Okay? We had to replace all q dot by in terms of p. Okay, here in the final transformed Hamiltonian, wherever you have a small q and a small p, you have to write it in terms of capital Q and capital P. Okay. Okay, I'll just give you one more question. Right. The last one, okay. We have got consider the linear harmonic oscillator with h is equal to half p square plus omega square q square, and the generating function f is equal to half omega q square cot 2 pi q. Okay. Right. Okay. So how do you do this? The question is find transformed Hamiltonian. You find the transformed Hamiltonian. You see that the generating function does not explicitly depend on time. So the transformed Hamiltonian is the old Hamiltonian. It's invariant. Okay. But you have to change the functional dependence. Okay. So for that you find P is equal to, so this is f of q comma q. Okay. So you see that small p is equal to dou f by dou q, and that's equal to omega q cot 2 pi q. Okay. And you see capital P is equal to minus dou f by dou q, and that's equal to what's it? Dou f by dou q. We got a 1 by 2 there. Okay. So it is 1 by 2 omega q square, and you have got minus cosecant square 2 pi q multiplied by 2 pi. Okay. So that becomes, that's equal to minus omega q square cosecant square. Oh, not this 2. This is inside the argument. Okay. 2 pi q multiplied by pi. Okay. So let's say omega pi q square, pi omega q square. This here, capital P. All right. Now what you need is you need to write small q and capital, small q and small p in terms of capital Q and capital P, and then just substitute it in this Hamiltonian. That will give you the answer. Okay, you can complete it. Right? Complete it. That's the homework. Okay, I think it's not very difficult. Okay, just find small q and small p in terms of capital P and capital Q. That's all. All right. So from here we can find small q and substitute that small q here. We'll get small p in terms of capital P and capital Q. That you substitute in this Hamiltonian, you get the answer. Okay, you don't have dou f by dou t, so that's also fine. Okay, and yeah, that's enough for today. Okay, thank you. If you have any questions, you can ask. I think we can stop now. Okay, thank you.